Anybody have any questions? 22.7, is that what I heard?
Yes.
C? Part C? Okay. So it says determine where the following functions are differentiable. Anyway, so I would suggest that you could probably do this by thinking about where you might have problems with differentiability. Okay, so 4x is differentiable everywhere. It's a polynomial. Anytime you have a regular old polynomial, those things are differentiable everywhere. Okay, you never need to really worry about it. The problem that we have could be with that square root, because what happened last time with square roots? First, it's not defined for x less than 0. And we also had a differentiability problem. What happened and where?
When it goes straight, it doesn't follow the full function in there.
So where is that for x equals what?
0.
At x equals 0, there was a problem. When we looked at the slope of the tangent line, or the instantaneous rate of change there, we had a problem because that slope ends up being infinity, right? Or really doesn't exist when we take the limit. The limit doesn't exist. So as we were taking the limit of the slopes, they were just getting bigger and bigger and bigger as we picked points closer and closer to 0, right? So the limit didn't converge. The limit blew up and went to infinity. So the instantaneous rate of change here at 0 is infinity, okay? It's not a number. So at this point, it's not differentiable, okay? So wherever we have differentiable functions, if we add them or take linear, what we call linear combinations of them, just add them or multiply by a constant and add them, then those things are also differentiable. So really, the only problems we have are with pieces that are not differentiable. So we can kind of look at these in pieces. So if I say, where is this entire function differentiable? Well, it's not even defined for anything, any value for where x is negative, right? Because square root of x wouldn't make sense. And in addition, it's not differentiable at 0. right? Right? So the only place it is differentiable is when x is greater than 0. Okay? We can also see this if we try to take the derivative, and then we look at where the derivative is defined, right? What's the derivative of this function? So what's the first thing we do to take the derivative here?
Change the square root of x to 1/2.
Great. Change the square root of x to x to the 1/2. And then we're going to take the derivative of each of these pieces. We're going to take the derivative of 4x, and we're going to take the derivative of x to the 1/2. Well, what's the derivative of 4x? 4. Great. What's the derivative of x to the 1/2?
1/2 x is negative 2/3.
Careful. So close. Negative 1/2. Right. So very close. So 1/2 x to the negative 1/2. Great. Okay. So what do we see as a problem? This negative 1/2 right here. That negative 1/2 means that we really have an x in a denominator. So immediately we should look at this and say, this function only exists for x greater than 0. So the derivative only exists for x greater than 0. So that's just the second way of looking at the same problem. Okay? Alternatively, we could actually go back to the limit definition and look at that, but these are both visual arguments and algebraic arguments. Okay? Any other questions? Yeah.
23.3.
23.3. Part A, right?
Yes.
So it was find the equation of a tangent line at x equals 1, right? For f of x equals x to the 3x to the 10th plus 2x to the 5th plus x plus e to the x. Okay. So to find the equation of a tangent line, we're going to need two things. We're going to need a slope and an anchor point. So here is the equation of a line. We need a slope. I'm going to do that in my first step. In my second step, I'm going to find an anchor point. So this is a point that I know my tangent line is going to go through, right? Okay, so the first thing I do is I find slope. Well, what is slope? Slope is the derivative. I'm not just finding the slope, I'm finding the slope at 1 in particular, right? So once I find the slope everywhere, then I just plug 1 in, and I have the slope of the line I'm looking for. Not just any line, but the slope at 1. Okay, so what is f prime of x? Well, I'm going to take the derivative of each of these pieces. Okay. What's the derivative of 3x to the 10th?
30x to the 9th.
30x to the 9th. Great. Oops. That's not a beta, that's a 30. What is the derivative of 2x to the 5th?
10x to the 4th.
10x to the 4th. Great. What is the derivative of x? 1. Right? The line like this, slope 1. What is the derivative of e to the x? E to the x, good job. Okay.
Wait, is this 23.3?
Yep, 23.3a.
There's no e to the x.
Is there not? Oh, I'm sorry, I'm doing 23.2. Sorry. Well, it was good practice anyway. Okay. Sorry, I looked at the problem, which is almost exactly like just above it. Okay. Thank you, Michaela. I want to know not just the slope everywhere, I want to know the slope at x equals 1, so I plug x equals 1 in here, and I get f of 1, so I get 30 times 1 to the 9th plus 10 times 1 to the 4th plus, plus 1, right? So I get 30 plus 10 plus 1, 41. So my slope is 41. Right? Okay, the second point I need is I need an anchor point. I know that my x-coordinate is 1. The question is, what is my y-coordinate? Well, all my y-coordinate is, of course, the function output of 1, right? I go back to that original function, not to the derivative. The derivative at 1 gives me my slope. The original function at 1 gives me my y anchor point. So I go back to my original function, which was 3x to the 10th plus 2x to the 5th plus x, or plus 1. And I get 3 plus 2 plus 1 equals 6. So my anchor point is 1, 6. Okay? Yes.
Oh, this So the end right there is 3, 1, 3 times power plus 2, 1 to the power, then
Plus 1.
Plus 1.
Yeah, sorry. Sometimes the pen's a little something. Okay, so then I go back to my function. I'm going to incorporate both of these things. I've got y minus equals x minus thing. And I'm going to plug both of these things in that I just got. My slope was 41, and my y-coordinate at that point is 6, and the x-coordinate is 1. And that's it. I can simplify from here if I want, solve for y, but this is adequate for me. Okay? Done. That's the equation of the line tangent to that function at 1. Make sense? Any other clarifications needed?